To the best of my knowledge, this is a summary of tensors and its related stuffs. And I'll just start off with the definition of basis, components, initial notations, and tensors. Alright, and therefore, I have a body over here. I decided to analyze this body with this reference space. I call this the I space. I zoom this out a little bit. Alright, if I zoom this out a little bit, I make it something bigger. And then I introduce the basis vector. And the definition of the basis vectors is simply the unit vectors in each of the direction, x, y, and z. And instead I'll call this basis vector e1 hat, e2 hat, and e3 hat. Alright, with individual magnitude of 1. Alright, individual magnitude of 1. So they are just simply unit vectors. So far so good. This is the basis vectors and definitions of the basis vectors. Okay, and therefore in the I space itself, we have defined the basis vector. Now as for the J space now, maybe for different colors, we decided to analyze things with a different reference point. I call this the J space. Alright, so we have a different set of basis vectors for the J space, which has its own E1, E2, and E3. And this E1, E2, and E3 their direction is different from these directions in the I space. Alright? Because as you can see, the whole basis thing, or the whole directional system, is being tilted in this manner. Now, if I have another reference point or reference analysis space, this is K. And therefore I'm analyzing things in the K space now, with their own individual set of E1, E2, E, and E3. And therefore this is the so-called the understanding for basis vector. And now let's talk about, or perhaps let's introduce with another something. Alright, let's give it 1 and 2. Alright, let's just label to make that coordinate. And I have a vector in this manner. Alright, this is a vector, I call it u underscore. And this u underscore is comprised of 2 times e1 hat, correct? Because you're gonna times 2 of this basis vector, and then 2 times e2 hat in order to reach this vector. Alright, so if I were to write that down, I will have 2 e1 hat plus 2 e2 hat, correct? In this 2D plane, correct? And instead of writing 2, because I want to generalize things, I write it in terms of u1 e1 hat plus u2 e2 hat. And this u1 and u2 are simply the components of the tensors. Alright, while the e1 hat and the e2 hat are the basis vectors. So the components are simply the scalars of the basis vector, that's all. That's the meaning of it. Alright, if you were to go 3D now, because in this video I can't actually show you 3D, because you see what I draw is always in terms of 2D. So I cannot do 3D. Alright, and therefore, for example now, let's include the E3 now, alright, the E3 hat. I can just simply say that, alright, maybe I shall write this here. Alright, just simply add in the new dimension. I'll have U3 E3 hat. Alright, this is also another component. If I have 4 dimensions, I have E3 E4 hat, something like that. Alright, and the components is always represented in terms of wherever your vectors that you have done, u1, u2, u3. Alright, these are the components of the vectors. And in order to represent this u1, e1, e2, e3 in a shorter way, I can use the summation rule. Alright, from I is equals to 1 to 3. we have ui e I hat. Alright, so as you can see, this is u11, u22, and u33. So as for this, it's just simply subbing I as 1, 2, and 3, and we can get this. So this is just the summation rule. Alright, and because the unit vector is always having the magnitude of 1, right, we can also rewrite this thing as just ui. Alright, and it depends on how many summation you want, how many dimensions. If it's 4 dimensions, then it's u1, u2, u3, u4. Right? So in other words, this vector we can just say that it's ui. Also can. Right? So they are the same definitions. Okay? And therefore, if we were to come back to this thing right now, we can represent this 3D space in terms of ui. Likewise, we can represent this j space in terms of vj, and then we can represent this space in the k as wk. Alright, and you may find that this is pretty familiar now. Alright, it's the I and the j and the k. Each of them has an initial notation. Alright, they have one initial notation. This is initial notation, and this is the starting of introducing the tensor concept. Alright, if I have, okay, so the definition of tensor, alright, is equals to 3 to the power of the number of initial notation, where p can be the number of initial notation, it can be the rank, alright, for independent rows of it. Alright, just call it rank will do. Alright, or you can call it the number of degrees. So there's many forms of saying. Alright, but in this case, let's use the number of initial notation. If I have one initial notation, I have 3 to the power of 1 is equals to 3. And therefore, simply say, in this scenario over here, if I want to represent a 3-dimensional vector, this is simply a vector. So 3 to the power of 1 is just simply a vector, which in this case is u1, u2, u3. Simple as that. Now, if I want to interact, alright, if I want to interact I, the space in I and the space in j, meaning ui and vj are interacting now. Alright, what do we have? We have ui, vj. Alright, and it depends on the multiplications that we're gonna do. Right, if it's a dot product, or we can call it the inner product, the outer product, or the cross product. The inner product is simply UTV, alright, or U transpose T, because it's inner, it's inside. Or the outer product is simply UI VJT, where the transpose is outside. Alright, and then cross product is simply this thing. Alright, so the interaction of this, of how you're gonna deal with certain interactions between spaces I, J, K, we're gonna deal with different stuff. For the inner product or the dot product, so this is the dot product, you have a scalar. For the outer product, which is the dyadic product, often you'll come up with matrices 2 times 2, be it 2 times 2, it may be 3 times 3, 4 times 4. It's always a matrix. And in terms of cross product, it's always a vector, perhaps k1, k2, k3. Alright, it's just a perpendicular vector to u and v. Alright, and now let's take a look into the dyadic product. Alright, so we have zoomed in quite a lot. So to speak, the UI and the VJ, when they interact using the dyadic product, we can give us some sort of a understanding, which we know that UI can be in terms of UI EI hat, alright, multiply, meaning tensor product or dyadic product, which we have just said earlier. If you don't know anything yet, it's okay. Alright, it's just applying the operations, that's all. I rearrange certain stuff. Alright, this is V actually. I rearrange ui and vj together. I have ei dialectic product with ej. This system itself sets a matrix of 1 1 1 1, or perhaps 1 1 1 1 1 1 1 1 1. Okay, so this thing is setting up a somewhat a structure for u and v to set in, or in other words, this whole thing is just simply ui vj. That's all. Alright, if you want to talk into how the spaces are interacting, this is how they interact. Okay, I'm not going into details, but I just want to show you that ui vj is somewhat being derived like that. And therefore, in this scenario, I can rewrite the ui vj as wij. Alright, if it's wij, then this is a second order tensor, or in other words, there is two initial notation, and by definition 3 to the power of 2, we have 3 times 3 matrix, and this is why the matrix 3 times 3 matrix comes from here. Alright, this dialectic helps us to create a matrix for us, 3 times 3. Alright, and therefore if I were to interact with another space in K, alright, u, v and w, alright, u, v and w, ui, vj and wk, just take note that just now what I've written in the w itself, alright, maybe in over here, alright, this w is not this one. It's not, okay? I actually forgot. Maybe I should represent this w as a, right, not to confuse things. So it's aij, okay? But let's continue back to this wk stuff, right? So if I want to interact with this thing, I can use the dyadic method. I have ui vj wk, alright? And can rearrange as bijk. So I have 3 initial notation right now. So as you can see, the initial notation is to help us to specify what are the interactions between this space and this space and this space, how they are all interacted, alright, between each of the reference space that I would say, or the basis vectors. So the basis vectors are often used, alright, it's often used. So to get back here, alright, u1, u2 and u3 are simply the components, e1, e2 and e3 are the basis vector, alright. So graphically, the basis vectors are the green color one, alright, while the components are simply how many times, alright, how many blue colors are there, alright, the components are how many blue colors are there, while the vectors is the red color one, alright. If you don't know anything, you just click back to the few minutes ago, alright. And therefore the tensors, the initial notation is I, alright. If you have a system that is bijk, you're talking about the interactions between 3 spaces, three of the spaces, I would say. Okay, now if you were to take a look more clearly, is that the components are built on by the vectors, I would say, is built on by how many basis vector, right? Because the components itself is how many times the basis vector. So the basis vector is very important, and therefore we're going to extract the basis vector out. So we're going to extract them out right now. And this is where we came with the second part, alright? The basis vectors being utilized to conduct tensor operations. I'll do this quick, so at least we'll save a bit time. And therefore, know that ui vj is the interactions between the I space and the j space, alright? And therefore we can also rewrite them as ui ei hat and vj ej hat, each of them in their own spatial system, alright? And these multiplications can be in terms of 3 systems, alright? As we have just said earlier, we can have a dot product, which is the inner product. We can have a dyadic product, the outer product, or we can have a cross product. Okay, so similarly, alright, I can just sum, because constants vj and uj are just some components or some multiplications or scalars, so I can group the scalars together. Alright, similarly for the rest of the dyadic product and cross product, I can also sum it up together, right? And what I have is, well, the rest is simply the interactions between the basis vector again, right? And this is the dot product, so we have a dot product over here. So this is a dyadic product, and this is a cross product. So the constants are, the components are always the same, while the basis vectors changes. Okay, when you conduct this certain operations, I can rewrite this form. Alright, let's extract. I can rewrite the dot product as the canonical delta. I can rewrite this. Actually, I don't need to rewrite this. This is just simply some matrix dependent on how many i's and j. Okay, it's just 3 times 3 lah. Okay, and then if it's a cross product, we have just a 3 times 1 matrix. I mean vectors. Alright, so it will be have ek, maybe some other perpendicular matrix. I mean vectors. Okay, or I will call this in fact I'll just rewrite this as eijk. Alright, and then ek. Okay, this k itself is not the same as this k. Okay, please take note. Alright, or maybe I should rewrite this. Yeah, I should rewrite this, so in order to not to confuse you, I write it as z. Alright, so I have ez hat. And therefore this thing is simply the Levi-Civita. Alright, and this thing is the canonical delta. Then I can just simply sub them in individually. For this part, I think I just repeat again because I don't know whether did I record it. Anyway, so this portion over here, I keep it the same. I simply rewriting all this so-called the basis vectors into all this. Alright, and the outcome is simply scalar, matrix, and a vector. Alright, the scalars is in terms of 3 to the power of 0, which is a 0th order tensor. And then for a vector, this is power to the power of 1, which is the first order tensor. And second order and higher, we will just say it as normal tensor. In this case, it's 2, so it's second order. If it's 3, then it's 3, it's third order, and so forth. Alright, and then here we are for the basis vectors. Alright, the tensor operations. We'll talk about the multiplication part only. For the addition and contraction and differentiation, I think you know already, so I'll not go through it that detail, or totally I'll not go through it at all. But however, now tensor group operators, right? But still, I'll recommend you just watch back the videos on the stuffs, alright, especially contraction. Alright, now let's go into tensor operators. As we know that how powerful is the basis vector, so we're gonna still go back to use back the basis vector. But before I go there, I'll just give you a graphical point of view of all this 0th order tensor or first order tensor and things like that. Alright, for a first order tensor, I wrote 0 order tensor, 3 to the power of 0. You know that it's just some numbers, scalar, just call it constant c. Alright, just some numbers. If it's a 3 to the power of 1 first order tensor, it's just some vectors, 3 to 1, some line. Alright, if the second order tensor, then we will talk about this one. We have a cube. At each of this surface, alright, perpendicular to the x, perpendicular to the y, and perpendicular to the z. Alright, each of this surface, there is 3 surface. Alright, we can illustrate this 6. You may wonder, the cube is 6-sided. Why am I representing in terms of 3? Alright, so because in the x, perpendicular to the x, perpendicular to y, and perpendicular to the z, this is the top plane, this is the bottom one. They are just in terms of the z-axis. So we can just illustrate in terms of 3 3 surfaces, and that's all. Alright, and therefore 3 surfaces, each of them has, you see, 3 individual components, and I will call this the directional analysis part, or basis vector, or so far and so good. Anyway, so each of these surfaces has 3 of these individual so-called basis vectors to work on. So it's just simply 3 times 3. Alright, so theoretically we couldn't say that it's 3 surfaces times 3 of the basis vector. We cannot say that, we don't say that. Alright, but just to let you know that this is the graphical of 3 square. If it's a 3 third order tensors, we'll have instead we'll have 9. We actually break it down. Okay, we actually break this down into 9 more parts. Alright, and we will analyze each of this part with individual axes or vectors, and therefore it's 3 times 3 times 3. Alright, so 3 times 3, if you take a look, is the interactions of maybe u, v, j, right? Is simply aij, correct? It's this thing. And when this tensor is being operated on another vector, alright, for example, we have a aij now. I operated it on a certain vector, I call it k. Now I will have bijk, which is 3 initial notation, third order, and therefore I have this outcome. Right? But this isn't just the case if you were to go to 4th order tensor. Alright, 4th order tensor doesn't mean that each of this is 3 stars over here. This isn't the meaning anymore. For 4th order tensor is gonna go into 4 directions, right, which is more complicated, which I'll not go through here. But generally, this is the concept of how the tensor is being applied, and such that it is being applied in finite element. Alright, and having to know the concept of this basis vector in terms of the multiplications and its operations, we can just finally come back to here now, alright, for the basis vectors, or how it's being used. Alright, so if you were to go back to here right now, alright, this is the old standard way of representing the U space, alright, the UI. Now we want to represent how certain stuff, let's say this body, up till a certain time, until a certain time it will deform. Alright, so we want to measure the position. Right, perhaps at this point may be moved into this point. So we want to measure the position across a certain time. Alright, and therefore we want to look at things that changes. Right, when we look at things that changes, we're gonna use back this basis vector. Now I gotta just write things in terms of basis vector. Now, because it's gonna change across time, alright, it may also change across its reference. Alright, so perhaps this is the basis vector. Across this reference, it may actually move to this point. Alright, and therefore this may change across certain time. Alright, I know that this explanation sucks, but anyway, so the concept of applying the basis vectors is just to partial differentiate it in terms of its axis. Okay, and therefore we have come out a del operator. Alright, this is called the del operator, and del operator is being applied. Alright, is being applied into this. So using the basis vector, you partial differentiate in terms of its own reference axis. Alright, the del operator is being born over here right now. Alright, if you were to multiply with a function, alright, this function may be in terms of x, y, or z. Perhaps you can say that 2xy plus z squared is a function. We can call this a scalar function, and therefore if you do that, you're just doing a gradient analysis. Alright, if you were to multiply with a vector, maybe 3, 2, 1, 5, 6, 7 or whatsoever, you're talking about divergence. If you were to cross product with it, you will have a curl. And this also explains the tensor operators for, in other words, this portion over here. Right. Therefore, I hope that this is a pretty straightforward understandings to give you a 26-minute summary of all about tensors. Not all, but rather than a conceptual understandings. And yeah, goodbye.